huge pleasure today to be able to introduce James Hamilton. James is an old friend who's had many careers. He was 10 years at IBM, then he was 10 years at Microsoft, now he's 3 years at Amazon, so they've got another 7 to go, but that's plenty of time to do exciting things. James was originally a database person and has then moved into operating very, very large services and now into being really a world's leading expert on large-scale data centers and sort of internet-scale storage, which he's going to talk to us about today. So James, thanks so much for being here.
Thank you. Thanks for coming in. And Ed, thank you for sending all the students that you do send our way. It's awesome having such a fine institution in our own city. It's wonderful. I joined the storage world probably 25 years ago. One of the things that I was just astounded at the time is the pace of innovation was awe-striking. I mean, we were completely rewriting DB. I was lead architect of DB2 at the time. We completely rewrote the storage engine to be per connected user per thread rather than per process. Major architectural change. We improved in one release the performance by a factor of 10x. We did 4x the next release. And what happened is, as time went on, we entered a phase that I jokingly refer to as the Dark Ages. And the reason I call it that is the number of database code bases, number of viable companies that could actually make money and be relevant was shrinking over time. And the code bases were bloating over time to the point where 4 million lines of code was a small base and an engineering team no longer fit in a single building. Things are moving incredibly slowly. Lots of the releases I was involved with shipping, I really am not positive it delivered a huge amount of customer value. Things have changed recently. What's happened is the pace of innovation's picked up again across the entire industry, specifically in storage. Big changes are going on. Number one, we've got more relational database offerings than we ever had before. Number two, we've got NoSQL offerings, more than possible. Number three, there's distributed storage and distributed block store systems. 4, we've got all of those happening in the cloud as well at a scale that is absolutely awe-striking. It's a really healthy time to be in storage. And so what I want to talk about today is some of what changed, why it changed, the impact of cloud computing, and then some of the challenges we face along the way. I'm going to start off by talking about some of the big changes that are happening right now in the industry and what's driving them. This is in the database world, what's happened is one size does not fit all. For a long time, the reason the number of database manufacturers was squeezing down was because customers didn't want another database. Once they have one, they have to administer it. Because they're so obnoxious to administer, and we did such a miserable job of making these systems usable, they really only want one, they can only accept one. So that's changed. What's driven that change, Stonebreaker is probably the leader of driving that change, but it's happening across the industry, and that is, if you can make something 5% better, nobody cares. If you can make something a factor better or several factors better, they're willing to take the pain. And so first thing that's going on is you can make database management systems much better than the big three. And so there's suddenly opportunity. That's number one. Number two, a lot of the decisions we made 30 years ago are no longer valid. The world's changing. Memory sizes, for example, are exploding. I gave an example here from the disk drive world. I always like to normalize numbers so I can compare them in a meaningful way. If you look at, in a relational database management system, what you care about is the I/O rate that you can drive. How many IOPS can I run? And so I've normalized it to gigabytes and say, listen, if you look at a 1990 Seagate disk, you can run around 37.5 IOPS per gigabyte. Today, you can run around 2.5 IOPS per gigabyte. That's a bad story. That says whatever you did, the assumptions you made 10, 15 years ago are just fundamentally wrong right now. And it happens in a variety of interesting ways, and you'll see that number drives a bunch of decisions in the industry. One of them is when an optimizer is trying to make a decision between should I do random access to a table or should I table scan? Used to be, if you were going to point access more than 30%, yeah, you should probably table scan. That number's been rapidly squeezing down, and it's almost always the right answer to table scan if you're doing anything interesting at all. And so all those optimizer statistics are constantly changing down all of the time. Second thing is, Plunging cost of computing changes the world in a pretty fundamental way. And I'm going to talk more on the plunging cost of computing and cloud computing because it has a big impact on what's possible. Plunging cost of computing. I've argued for a long time that this happens in the data analytics and warehousing world. And it goes like this. It says, if you look at some of the really high value workloads like hedge funds, financial analysis, oil field management, almost whatever computing costs you have to run it. Walmart was running really, really amazing data analytics back 15 years ago. It didn't matter what it cost because the value of what they're optimizing for was so high. What happens as the cost of computing falls, the number of workloads that are worth more to run than the cost of computing goes up. And so the beautiful thing about computational X, where X is almost anything you want, is as the cost of computing goes down, the number of things that it's worth doing the analysis on goes up. And so regional grocery stores can afford to do that now. Even very small companies actually have to do that now. If you're not doing that, if you're not understanding your logistics chain, if you're not understanding your customers' buying patterns, you're actually going to go out of business. And so as the cost of computing falls, the value or the number of workloads that make sense to run analytics on skyrockets. For years, I argued that this didn't apply to online transaction processing systems because OLTP systems typically scale with real-world entities. They scale with customers, or page views, or purchases, or SKUs. They scale with something that's real. But in fact, even that's not true. In that computational trading systems and other machine-to-machine transactions, in fact, scale again with cost. The limiting factor is how much does it cost to do it, and how much is a transaction worth? As the cost of computing falls, the amount of computing goes up. And so it's a wonderful time. There's changes happening in the industry that allow us to fundamentally reduce the cost of computing, which means the amount of computing is skyrocketing, which means the value we can deliver is skyrocketing. And so that's the first big driver of change. Second big driver of change is cloud computing really is something different. I pride myself in trying to recognize when a trend is a yawner, it's going to come and go again. I never learned Corba. I think it was probably a good call. Cloud computing, something's here in a fundamental way. It really is going to change the way things are done in a very fundamental way. And so a couple things that cloud computing and in general internet scale computing drives. And one of them is instead of the data center or the IT group being a cost center, it is the center. If you look at an insurance company or a retail grocer, everyone needs computation. Everyone has to have storage. Everyone has to have administrative systems. That's just a cost of business, and you hope that what happens is as the revenue grows, the cost of the IT shop doesn't grow at the same rate. That's about all you care about. And you say, how much innovation do you want there? Not much. Just don't screw up is basically the way it's always played out. Not the most exciting place to work. Well, let's look at the value of infrastructure in a business like where I work at Amazon Web Services. The difference between Amazon Web Services being a tax on the company that can never ever deliver great revenue versus an absolutely economic machine that is producing enough revenue to be reinvested into the business so that we can be innovating and producing new services to help customers and at the same time drive down prices 11 times in 4 years, which is where we are. The difference between those two ends of the spectrum is 100% infrastructure cost. That's all that matters. And because that's all that matters, what do you think happens? Well, you try to be very good at it because that is your industry. That's what the business is. Nothing else matters. And so we have power distribution experts because at scale, if you can save 0.25% of the power, it's worth doing. It's absolutely worth doing. We have server designers. Why? Again, small gains, big numbers. It's a wonderful place to be. And so instead of where it used to be difficult to justify innovation, it's hard to justify not innovating. It's actually, if you don't have experts in a given area, you're nuts. You're absolutely nuts because think about this, at this scale, If you're not doing something that's a little bit better, if a fully loaded $150,000 salary is going to return millions at scale, you just got to do it. And so suddenly all the rules change. It suddenly becomes super easy to justify new things. Anytime you get a chance to change the cost of the business, it's worth doing. And it makes it a really fun time. That's one of the reasons why it's so much fun to work in our industry right now, is for probably the first time ever for me, all these ideas, we're bounded only by the ability to implement them. Just having enough IQ available quickly enough. I wanted to talk about scale. We put this number together because there's so many ways to talk about scale. There's just so many ways to talk about scale. We can talk about number of megawatts, number of servers. Most of those numbers we can't release anyway. And so what we did is we said, listen, Amazon in the year 2000 was a $2.7 billion business. That $2.7 billion e-commerce business ran on a certain amount of infrastructure. How frequently do we bring that infrastructure online in EWS? I was hoping it would be 4 to 6 weeks. It's every day. It's a shocking number. It's a shocking number. Today we will bring on enough infrastructure to support Amazon in the year 2000. And we'll do it again tomorrow, and the next day, and the next day. Think about the rate of just trucking racks of computers to data centers and how fast they have to come off the trucks, be delivered into the center, and lit up. It's just a shocking number. Forget everything else that's going on. Just hitting that number is interesting all by itself. And as soon as you see a scale number like that, it means, ooh, think what's possible. Small gains, big possibilities. Like, for example, just to give you an idea of scale, I offered once to work for nothing. My only salary would be the systems that I can recover that weren't operating in our data centers. And the reason for that is I knew we had an inventory problem at the time, and I knew there was enough compute infrastructure out there to pay me extraordinarily well just harvesting it. And what I was arguing for, of course, is let's go fix that. And we have. So, numbers are big. Okay, so one of the things I do every 2 years is I go and recalibrate where does the money go in the data center chart. And the reason I do this is I want to work on the problems that are at scale, and the biggest problems is where I want to focus my time. If you solve 50% of a 2% problem, nobody cares. If you solve 2% of a 50% problem, everybody cares. And so I want to work on the 50% problems. Second reason why I do this is what I've learned is a lot of what you hear is garbage. It's just wrong. People talk about how things work, but they haven't a clue. And it's partly because some people that are working in at-scale data centers don't study them closely enough. And it's partly because a lot of people don't work at at-scale data centers. And so getting the data on the table once in a while is worth doing. These aren't exactly the numbers that you could produce at a Google or Microsoft or Amazon. These, because I can't show those numbers, but what I can show is if you went to a consultant and built an industry-leading data center today, which is better than 95% of everything out there, you'd get this. On the comparison side, people make crazy comparisons because they try to normalize things that have very long life, and not normalize them, pardon me, compare things with very long life, like a data center of 10 to 15 years, and compare it to a server with a 3-year lifetime. And people say, oh my God, the building costs more than the computers that run in it. Well, not true, and probably not relevant anyway. Like, I'm not sure we care. So to normalize them, what I've done is I say, listen, let's assume a 5% cost of money. Let's take the amortization period of a data center at 10 years, servers at 3 years, networking at 4 years, power I'm going to pay every month. I'm going to take everything and I'm going to say I'm going to pay a monthly fee against all of my costs. And now they all compare. So 2 things pop out right away. The first one, you say, James, where's the people cost? I've read that the number one cost in enterprises are people, the administrative costs. Where are they? Super interesting thing. They're not here because they're not relevant. What happens, it's really interesting. In an enterprise, when you have one Oracle system, 13 SQL Server systems, 50 SharePoints, 3 Oracle 10s, is you take care of them by hand. You have no choice. You can't afford to it's a low scale. You can't afford to automate. There's nothing you can do. And so people costs do dominate. When you have 1,000 or 10,000 of every one of those things, you couldn't possibly hire enough people. There's not enough people on the planet. It's just you cannot get enough skills. And so you have to, in fact, automate. And it comes back to scale economics. If you take pain and transfer it to the development team, you do it once. If you leave it in operations, it scales. You can't leave it scaling, so everything has to be automated. It's a wonderful place to work because you don't want, nobody wants to get involved with repetitive infrastructure. And the other problem with repetitive infrastructure jobs is people get it wrong. You invariably hire smart people to do boring jobs. You give them a boring job, they make mistakes all the time. If you only give them really, really good jobs, really hard problems, which is when the automation fails, they do good work because they have to think. And so there's a bunch of reasons why you really want to get the administration out of there. So the first thing is administration's just not there. I ran a service of $27 million revenue service, small service. Our cost of administration, if you added up servers, data centers, ingress, egress, networking inside the data center, administration, all the cost of running the service was 9% administration. At scale, done well, that was not done well. At scale and done well, it can be under 3%. So the first thing you learn from this is don't worry about the people, it goes away. Interesting behavioral change. If you said to an enterprise customer, hey, I could sell you a big scale up server and I could somehow reduce your administrative costs slightly, but you have to pay a lot more for the server. They say, I'm in, I'll totally do that. If you come to Amazon Web Services or someone that's running at scale and say, listen, I could reduce your administrative costs by charging more for servers, are you nuts? There's no way we're going for that. I'd happily add administrative costs to save money on servers. Look at how much I'm spending on servers. That's a dominant cost. That's number one. I wouldn't trade that for anything. So completely changes the way the world works and the way you think about things. Let me give you a couple more data points. Second thing you hear, this is one of those ones that you hear things are wrong all the time. Second thing you hear is number one cost in the data center after people is power. Power is the thing that we have to focus on most. There's a variety of reasons why power is, in fact, super important. But if you look at this, it's not the number one cost, it's not the number two cost. Number one is servers. Number two is power distribution and mechanical systems, the gear that distributes the power and the gear that gets the heat back out of the data center itself. Power is number three. So it's just wrong, not true. It's absolutely not true. And so let's debunk another one. There's a few vendors out there that sell blade servers. It's a great innovation. You take a server and you turn the board 90 degrees, which I guess is more aerodynamic, maybe more efficient. What they're doing is they're packing a lot of servers into a very small place. What happens is it consumes less floor space. You have 20 kilowatts of power in a single rack, maybe 25 kilowatts in a single rack. So let's look at whether this makes sense or not. I'm saving space. That's the 4% number. I'm paying more for servers. That's the 57% number. And I'm paying more to cool them. That's the 18% number. Anyone want one? Not going to happen.
Why are you paying more to cool them?
You pay more to cool them because they're packed in so densely. For a given temperature of air, you either have to move the air a lot faster, more volume of air, or you have to cool the air a lot more, which is much more expensive. So it's one of those two equations. Neither one looks good. And so if you look at scale operators, 0 blade servers installed. That's why it doesn't make sense. Okay. One more observation from this, just to motivate some of the things that I'm working on right now. If you look at I love looking at ratios and how things change over time, and you'll see that keep coming up as I talk through this. Here's a ratio that I think is interesting. If you look at all the IT gear in a data center, all the servers, all the storage, all the networking, and you say, okay, I'm going to look at that number. If you plot the percentage of that number that's networking gear, it's going up. So what's happening is server costs are going down. Networking costs are in fact flat to going up. It says over time, networking is becoming the dominant cost in there. Makes 0 sense. Makes 0 sense. And so right now I'm spending about half my time on networking. Because whenever this kind of chart, this kind of model teaches you where the problems are. And if you can look ahead using that, you say, that's nuts. You got to do something. And so we will. By the way, that chart, I believe I could stare at that chart easily for a day and keep pulling things out of it that are interesting, either poking at the industry because I think that some people are looking at things incorrectly, or saying, look, this tells us that this is going to be a problem soon. Hey, Ed.
So here's what's interesting about this to me. It's a little bit like Moore's law. That is, you got this prediction about transistor density, and that then generates a prediction about a set of problems that have to be solved.
Yes.
It may be lithography, it may be heat dissipation, it may be a bunch of stuff. And since people then know what problems need to be solved, they set about solving those problems, and things move forward. And your pie chart is sort of the same thing. That if you dip this over years and you project forward, it tells you where to spend your energy.
Exactly right. In fact, we'll keep coming back to that. So going back to how do I look at things? I look at things as trends, and I say, okay, we're trending towards a lot more cores. What's the limit? What's going to happen? Andy Beckelheim has been saying, well, we're going to have 1024 cores in 2020. Okay, 1024 cores, it's a lot of cores. What's the limit? What if cores were free? What if I could have an infinite number of cores? What am I going to bump into? Well, the first thing is, does the program parallelize it well enough, blah, blah, blah. So that I get. So let's put that one aside. What will stop me from using infinite number of cores? And the first thing is getting data up to them. There's absolutely no point in running a core if you can't get data up to the core to actually do something valuable. So the first thing is communication costs are a limiting factor. And that's an interesting one because that applies to all levels of computation, across the data center, across the metro area, across the WAN, even within a single server. And what we're talking about here is in a single server. So communication costs are one limiting factor. And the second limiting factor is power. And so it turns out you can solve most of the problems with parallelism. And so if you run more lanes, you can get more bandwidth up to a processor. And Intel's playing that game right now where Nehalem went 3 memory channels. We're about to go 4 memory channels. And so maybe we're good. You see, no, we're not good. The reason we're not good is every one of those memory channels is pins that have to get driven off the CPU. And every time you drive pins, it takes power. Every time you try to communicate off chip, it takes a lot of power. And so the limiting factor is communications or power, and you're going to fight between the two of them. And so what it says is, the things that we're going to have to optimize for, we went back earlier, I said power is a number 3 cost. Turns out it is a limiting factor. It is interesting, but for different reasons. And so first thing we observe, power and communications, and that shows up at all layers in the system. Okay, so continuing on the theme and saying, well, we're having trouble getting enough resources up to the processor. This is some data produced over, I think it was 20 or 30 years by Patterson. And his observation is, if you look at just bandwidth, what's the rate that a CPU core is consuming bandwidth? In other words, in order to have it run flat out, what's the rate that you have to get it data? What's the rate that's improving at? So this is the rate that a core consumes power over time. And that's the climb rate. And then what's the rate that memory can deliver data up to the CPU? And that's climbing slower. And that's what's referred to broadly in the industry as the memory wall. Second observation, very similar observation, is you can't get data off disk fast enough. Even sequentially accessing, they don't come off disk fast enough. And so it says we have a problem between CPU and memory, and we have a problem between CPU and disk. And so let's look at what we do with each one of those one at a time. The first one is the memory wall. There actually are some very, very, very good-looking solutions to that. The short-term answer is just use more lanes. And it works to a limit, but it does consume power, and that's not one it does not scale infinitely over time. And so that's a bounded solution, but a good solution for the short haul. Over the long haul, the right solution looks to be chip stacking and through silicon vias. And through silicon via means you can communicate between 2 chips stacked on each other without driving external pins and without the power expense of communicating off chip. And so it's wildly less power intensive. There's some downsides to it. It's very heat intense. It's a lot of heat in a small space, and so you got cooling challenges. But IBM in the late 80s was still using emitter coupled logic in the system in the system 370, 3090s, and 38X series. And we know what happens. If you bring water directly to the chip, you can cool a furnace without too much trouble. And so this is a technology that is in use in cell phones today. There are some modern memory systems that are using chip stacking. There's some networking work that's using chip stacking. It's working well in the lab, and in fact, it is used in many cell phone technologies today. And so chip stacking and through silicon vias looks like a solution to the memory wall. We're going to be capable of coupling large memories with cores and be able to deliver data up the stack. And so I'm claiming this one looks pretty good. We have a short-term answer and we have a long-term answer, so this one looks pretty good. And we have some proof in cell phones that says it actually works and can be scaled and is economic. So I'm going to claim this one's more or less solved. Let's look at the disk problem. The disk problem, it's a good news, bad news story. Years and years ago, back when the sweet spot of the disk world was 750 gigabytes, I remember traveling with Jim Gay and visiting all of the disk manufacturers, most of which no longer exist today. And it was a funny story because what happened is they were all saying, 750 gig, that's tops. There's just no need for more capacity. All you're going to see is shrinking platter sizes and less platters. That's all what's going to happen. Well, you know that's wrong. I mean, we've got 3 terabyte disks right now. We've got 4 terabyte disks that are running well in the lab and will be here within the next 12 months. The disk industry looks extraordinarily healthy, and in fact, we have good line of sight through technologies like heat-assisted magnetoresistive or energy-assisted magnetoresistive bit pattern media. We've got good line of sight for the next 10 or 15 years to get continued density improvements. So absolutely not a problem. They're wrong. They're going to keep scaling on size. We have a huge appetite for it. We're going to keep buying bigger disks. They're going to keep producing them. No problem at all. So that's a good news story. Here's one that looked good for years, but it went away. And one of the reasons you've got to watch when you see a trend, and you have to be careful that you don't assume it can continue indefinitely. And so rotational speed, as you speed rotational speed, the bandwidth off a disk improves as the rotational speed goes up, and the time it takes for a given sector to swing under the head goes up as well. And so rotational speed's a wonderful thing. We went from 3600 up through 5600 to 7200 to 10K to 15K and then stopped. Why haven't we seen 20K yet? And it comes back to power again. Turns out the power consumption of a disk is cubically related to the RPM. Yikes. That scales up very, very badly. Second thing is, disks are this horrible analog device where some of them actually have as many as 3 processors on the disk itself whose only job it is to find the data in a disk that's orbiting, sort of spinning, sort of bouncing, moving back and forth, and the head's trying to track, and so they have a horrible analog mess. They're trying to find signal in that. And so there's 3 processors trying to extract signal from that mess. Well, as you increase the rotational speed, rotational vibration, and non-repeating runout gets worse. And so those are the other 2 reasons. My opinion is all unsolvable problems along those lines, we'll solve those ones. We actually could solve those. The problem is the power. The power will probably keep 20K from ever happening, and I'm skeptical that 15K is going to keep happening. I think actually 15K is going to go away. So this one, not such a good story. Next one is...
Sorry.
Yes.
You don't buy the highest performance processors, right? You buy the highest performance per watt or something like that. How about disks? Do you buy the fastest rotating disks, or do you buy down some?
On the disk side, we buy 0 15Ks. They're not economic. 15K makes no sense at all because it's not a very fast disk. It's not nearly as good a solution as NAND flash. And yet the expense just doesn't work out at all. And so we buy 0 15Ks. There are some SKUs where we actually do buy the fastest processor. There's a few places where raw performance really matters big, like high performance computing. And so there are a few places where we do that. But the normal thing for us to do is to buy a down bin. And the 2 reasons to buy down bins, one is they're more economic. And the other reason is Intel process control is way better than they admit, and so down bins are often very good. Okay. Whenever you're comparing 2 things, people always screw up and try to compare non-comparable things. And so if you're looking at random IOPS, random I/O performance, you measure it in IOs per second. And when you're looking at sequential I/O performance, you're going to measure it in megabytes per second. And they're not terribly comparable. So what I've done is I've converted IOs per second to megabytes per second so we can look at sequential growth versus random growth. I told you earlier sequential growth was too slow. We have a problem. It's not improving nearly fast as the processor is. So we've got a problem already. But the sequential growth is actually respectable. It's a decent looking curve. What's amazing is, take my word for it, the random I/O performance, it actually is a slope. It's a positive slope, but it's a tremendously, pathetically poor positive slope. And so what's happening is random I/O performance is getting worse at an incredible rate. And a 3 terabyte disk, which is the biggest disk available right now, takes 8 hours to read sequentially, which is already a shockingly long period of time. It takes a month to read randomly. If you randomly seek that disk, it takes a month at optimum IOPS rate. It's just completely impractical. And so Jim was 100% right when he says disk is tape. It is getting to the point where you cannot afford to randomly seek anything ever. And one of the reasons why MapReduce looks so good is, databases are working really, really hard trying to figure out exactly how to know all of the random seeks that are coming up and be able to schedule them in advance so you can run them in parallel. It's just nuts. So you can go 100x faster just sequentially scanning, so don't think so hard, sequentially scan. And where that wins is the percentage of the times where that wins is going up all the time. So this is a huge problem. And the solution, of course, is at the very high end of the market is where random IOPS is all that matters. Disk is dead. It's all going to be NAND flash and follow-on technologies. It's all semiconductors. There's none of it's going to be on spinning media. It just can't. It's just, these numbers, you look at that and say, that can't possibly work. Just simply cannot possibly work. And all of the optimizations in the database world that are focusing on making that random I/O disk device work well are kind of pointless. They just don't make sense. Okay, here's another one. I mentioned networking. I gave you a little bit of a forward look at this, and I said, networking, if you look at the cost of all the gear that goes into the data center, the networking gear is, even though you think Moore's law is going on, there's a bunch of great things, a networking equipment is basically the same thing as a computer. It's a special purpose computer, but it's basically just a computer. Everything should play out the same way, and yet networking gear has a relatively constant cost, and the cost of the servers is plunging rapidly, which is to say the percentage of the overall expense is trending higher and higher towards networking gear all the time. Absolutely broken. Just completely broken. So you say, well, why is this so broken? What's going wrong? Well, we've learned this in the past. Is in the old days of mainframes that I talked about earlier, the 1980 emitter-coupled logic IBM mainframe, IBM supplied the CPU, the central processor, IBM bent the metal to build the gear, IBM wrote the operating system, and IBM supplied some of the apps that run on top. It was a very safe world. Everything was very reliable, but it was pretty expensive. That is where the networking world is today. If you buy from Cisco or Juniper, Cisco selects the central processor unit, probably designed and built it themselves. Cisco bends the metal to make the gear, and the operating system that runs on it is theirs and theirs alone, doesn't run anywhere else, and you can't possibly run an open source solution, and there's no way you could ever put application code on there. And so there's just a variety of reasons why that's bad. One is these big vertical integrated monoliths that you can't plug and play. You can't replace components. If you're running Juniper, you cannot plug in Cisco. Sure, they're all using RFC, whatever, but it doesn't work the same. It doesn't manage the same. You cannot do it. Well, that means it's a very inefficient industry. So wonderful things happen. I've hated this for years. Wonderful things happen, and that is merchant silicon providers are now making the central processor in a networking equipment. That's called an application-specific integrated circuit. These are really complicated devices that are responsible for routing packets. And so there's now, Broadcom, Marvell, Dune, owned by Broadcom, Fulcrum, now owned by Intel, all produce competitive gear, and you're welcome to build to buy them and do what you will with them. Broadcom produces a reference platform. The reference platform is the bent metal. That's the actual finished router. And that switchgear is available from Celestica, Dell, NEC, Quanta, DNI, and many, many others. And they all compete with each other. And so you can decide if you want to buy any of those ASIC providers, and then you can buy the reference design from any of those suppliers, and then you can run an open source software stack on top of it. And so the world's changing. We're getting some of the same economics that are happening in the server world. And of course, what happens is we now get on the Moore's Law path. If you look at when we first started doing this, the sweet spot was a 24-port ASIC. Well, the vast majority of the cost of a router is the ASIC itself. The physical connections, the PHYs, scale with a number of ports, so I can't fix that. But the most expensive component stays about the same cost. A 24-port ASIC is identical cost to a 48-port ASIC, which is an identical cost to a 64-port ASIC, which will be an identical cost when it comes out to a 96-port ASIC, which means we're now seeing some semiconductor advantages where the cost falls over time. Another one is in the software side, what happens is most vendors charge by the switch or by the port count, and you don't want anything that scales with anything. What we want is we want an open source solution where you pay once for R&D, you have specialists that take care of the OS, or the protocol stack in this case, but you don't want something that scales with a number of pieces of equipment you're running. And there actually are viable open source protocol stacks out there right now. And so it looks like this world's changing. And for a few companies, Google and Amazon and probably a small number of others, this is happening right now. And I expect it's going to happen fairly broadly. There's going to be a lot of startup opportunities around this because not everyone runs at the scale we run at. And so there will be some companies that want someone else doing the engineering for them. But it just means there's the ingredients for many good startups in this ecosystem change. A couple things that are happening interesting on the software side. So if you look at the software side, there's open source routing stacks that are extremely credible right now. Quagga is one, Zorp is another that's fairly credible. Second thing is there's some new work going on called software-defined networking. There's been a bunch of papers over the last few years on basically centralizing network control systems and treating the routers as dumb switches, just doing routing. And basically what the observation is it goes like this, routers basically are, each one is an autonomous distributed system, and they negotiate effectively with a distributed algorithm to figure out what should be in which routing table. Well, that's great. I mean, if things don't run in the same administrative domain, it's a fine solution. But if every piece of gear is running in the same administrative domain, and if you know every server in the entire data center, you know where it is, then you can actually centrally control this. And the transaction rates that you'd have to run in order to deal with servers coming and going and routing changes is jokingly small. It's incredibly small. It's not a very hard problem. And so VL2 was one paper that headed down this path. Portland is another one. There's been many examples. Stanford Group has been doing some excellent work in software-defined networking, which is basically saying, listen, you need some protocol to communicate with the routers. Let's standardize on OpenFlow. And the OpenFlow is uninteresting in any reason other than there's critical mass behind it, and every switch provider is implementing it. And so what that means, even Cisco's announced that they're doing it now. And so what that means is that we don't care what it is, as long as there's some way to communicate with all gear regardless of who provided it. That's pretty interesting. So there's changes happening there. So in the switch world, we've got standard protocol stacks for open source solutions, and we've got software-defined networking looking pretty interesting. On the client side, we're stealing ideas from the high-performance computing world. And that is, today, if you're in a virtual machine and you want to get to a network card, you go from the app space of the guest machine down to the OS space of the guest machine, across to the hypervisor, and down to the network interface card. A lot of traffic, lot of expense, a lot of copying, a lot of moving data around, very inefficient. And so the first trick that makes sense is SRIOV, single root IO virtualization, allows you to map from a hard networking card, you can produce virtual NICs that are mapped directly into the guest space. So you can go from guest app space to the OS, straight to the NIC, no hypervisor. So that's the first thing that is happening right around now. Second one is there are many solutions that are stolen from the InfiniBand world. Rocky and iWarp are two of them for going from guest app space straight to the card. And the whole trick is getting latency out of the networking world. And so hard to know which one of those wins, and it probably won't happen in very high scale for the next year or two. But you can see where the world's going almost certainly. And so it means, again, opportunities for innovation are heading down that path for sure. Okay, MapReduce is a piece of technology that's kind of amusing, where the database folks generally are upset by it because it's rediscovering everything that was discovered 20 years ago by the database community. Well, that's maybe us in the database community rewriting history. It was actually, it's wonderful work because it scales. And anything that scales and allows human beings to run applications in parallel at very high numbers is an amazing thing. It was actually work done by Jeff Dean, alumni of University of Washington. And I love MapReduce because there's basically two languages that allow normal programmers to write parallel code. One's SQL. If you give SQL to a database engine, it can run it in fairly high scale and fairly well. A lot of parallelism. Another one is MapReduce. Normal people can write MapReduce code and run it across a 4,000 node cluster, and it works. And the reason why this has happened, the database community is upset by it, is databases don't scale. You cannot run the kinds of workloads that are being run at MapReduce scale. And so, because they didn't solve the problem, someone else did. It's a great thing. So I love this. And what's happening is there's a bunch of ideas from the database world that are worth pulling over to MapReduce, materialized views, things like that. And it's just starting to happen. Another one where the database community didn't do the right thing is the NoSQL movement. And because databases are hard to administer and don't scale very well, I was the author of some of them, and it's totally true. What happens is simple key value stores are popping up all over the place. And the reason is when you have to run at extraordinary scale, you're willing to give some things up. What's being given up today is actually more than I like. Most of these systems are eventually consistent. Most of them are not durable on commit. It turns out a lot of these, the CAP theorem argues, you have to give up something. You can't have consistency at the same time you have availability. Well, what happens with theorems like CAP is they get used to paper over less than detailed thought behind the engineering. It turns out it's totally true, but you have to always ask the question, how long is the moment of unavailability? And you can play games with, there's a lot of gray in there. This is engineering rather than theorems. And because there's gray in there, giving up consistency is totally hard. When x is equal to 3, you set x equal to 5, you read it a day later and it's equal to 3. It's a very confusing programming model. It's hard to write reliable systems like that. It's hard to write reliable systems when you write x equals 5, you check to see if x equals 5, it does. Then you check again 500 nanoseconds later, and it's back to 3 again. It's really confusing. And every one of those models happens in eventually consistent systems. And so there's a place for it. There's absolutely a place for it. The Dynamo paper said that a shopping basket actually is well implemented using eventually consistency. Totally is. There's just most of the world doesn't run well on eventually consistent. Super hard to reason about, and I'm arguing unnecessary. With good engineering, you can implement this kind of performance maintaining consistency. And it's really not that hard to do. And at the scale that we're running at, even though it's extraordinary, you don't have to give up a consistency. So I'd argue some of this is an overreaction. And in fact, highly consistent systems are useful and really easy to reason about. And what we need is a sliding knob where I can adjust the consistency level to what I need for my application. I hate to just give it up across the board. Last observation is client storage is completely, this is another place where disk is dead. We talked about high-end random access workloads are not going to be running on disk, period. They're gone. They're gone. Those workloads are completely not going to be running on disk. Here's another one. All clients are going to end up on NAND flash. Every client device is giving up its disk. Kind of tough for the disk drive manufacturers. I give them a hard time on this. But the truth is they're in wonderful shape because every one of these client devices is connected to a cloud, and every one of those client devices has more disks than it ever had in the cloud. And so, in fact, I think client devices are driving more disks than ever. They're not in the device anymore, but they're actually driving more disks. And so I'd argue this is actually the disk drive manufacturer. They gave up the high end, bad. They gave up the client, bad. But the client's still driving more volume than it ever drove. In other words, people are storing more than they ever stored before. So that's completely a good thing. And tape is incredibly hard to administer, has a lot of nasty operational characteristics. Disk wins that business as well. And so the disk guys are actually in great shape. Not a problem at all. Last observation. Go ahead.
So isn't this a problem in Amazon's that people are maybe storing more things in the cloud, but everyone's storing the same thing? So everyone's storing their music collection, a lot of overlap, and if you're smart in the cloud, you don't have to store many copies.
Great question. So the question is this a problem for Amazon, or is it a good thing for Amazon? If you store a lot of things in the cloud, there's a lot of redundancy across those things. And so could you deduplicate where you store something once and you're actually just storing references to it? Absolutely. It turns out a lot of the data that's stored in the cloud, there is redundancy, but there's just so much low-hanging fruit out there right now. The trade-off between running dedupe at a very high scale the trade-off goes like this. Dedupe at a high scale, it doesn't work well at small scale. You need it across a large number of users. If you do it at high scale, the indexes get very large. And so, in fact, the transaction rate you're running in those indexes, it becomes a fairly hard problem. The cost of storage versus the failure modes and some of the complexity of that makes dedupe can work, but it doesn't work across high access rate workloads. It works wonderfully for archive data. It's wonderful. For very cold data, it's worth the expense. For reasonably warm data, it doesn't look like it. So I'd say it's not a win across the board. Okay, open source and cloud influence. Now, the couple more things that are happening. One is cloud computing is driving down the cost of computing in a substantial way. Recently, I blogged. I came across this wonderful example where one company had done a 30,000 core cluster. And if you look at this thing, it's the equivalent of what a national lab would have done nuclear weapons research on, in fact, very few years ago. And I forget the exact price for this, but I think it was around something ridiculous, like about $12,000 for an hour, or something like that. Incredibly small number, where it's a national lab size supercomputer that's running at a cost that is what a fraction of a supercomputer would cost a few years ago. And so cloud makes a lot of things possible that weren't possible before. And whenever we talked earlier, when you drive down prices, what happens is the amount of computing goes up because it's worth doing. So first is cloud's changing the market in a pretty big way. And the second thing is the open source world. Again, that's more cost that isn't there. And as more cost comes out, more things are possible. So those are two influences that are pretty strong. That's what I wanted to cover today. Basically, cloud's driving innovation in a fundamental and substantial way. As the cost of computing goes down, the amount of workloads that are economic to run goes up. Third, networking costs don't make sense right now, so you're going to see big changes in the networking world. Four, the most difficult problems are all related to persistent state. And so the interesting research problems, at least from my perspective, all have to do with dealing with persistent state and what trade-offs to make versus eventually consistent, non-conventionally consistency. What kind of trade-offs make sense are the ones that are worth studying. And basically, it's an exciting time to be in the storage community. So anyway, thank you for your time. Appreciate it.
Is there a notion of how much disk CPU bandwidth is needed locally, like a maximal point? Because I mean, at some point, I can stream HD movies off my laptop now, so like, why do I need a terabyte drive on my laptop? I don't. So I was wondering, like, is there a notion of where we'll see a plateauing of what we have in the client? Because why not just offload it to the cloud?
Yeah, I think when it comes to multi-terabyte disks, people aren't going to be carrying them around in client devices. They will all go up in the cloud. And with respect to the amount of storage that you'll have accessible by the client device, I think that'll keep going up and just continuously, without change. You asked, is there a set of ratios that make sense?
I mean, and obviously CPU and other things would go along with that as well.
There are it changes across workloads, but for a given workload, yeah. In fact, the high-performance computing world specializes in understanding that for a given algorithm, you need this ratio of memory to CPU, and they're able to size systems super reliable that way. Of course, it doesn't work across workloads.
To what extent are these cloud companies constrained by the rather poor state of like residential internet service providers? I mean, the fact that the amount of bandwidth an individual can get at home doesn't seem to be going up that much.
Yeah, so the question is, how much is cloud computing constrained by the wide area network? And generally, the poor service in North America in homes. Well, the first thing is, in places like Korea, the service is awe-strikingly good. Japan's very good. So it's not a technology problem. It's a business structure problem where we're not getting what technology could be delivering us. So that's one thing. Is it a problem? You bet. In the business side, where it's just an expense, you can have as much bandwidth as you want. Even there, it is a problem for cloud computing. Mostly because if you're a startup, you just jump on the cloud and it's just not a problem. But for any business, they're going to spread some of the resources in the cloud and some of it on-premise, which means the distance between the on-premise and the cloud is a limiting factor, and what things you can afford to synchronously replicate or asynchronously replicate. And if you're running async, then how do you deal with the consistency issues, and what do you do in the case of a failure? That is a problem. And so that's another area. We talk about interesting research problems. How to get more, how to hide latency is super, super, super interesting. And how do you get more bandwidth for a given wire size? Super interesting. Yeah, it is a problem. There's a question.
So you said that you want a knob for consistency.
Yes.
Does it have more than 2 settings?
Does it have more than 2 settings? Yeah, probably it does. The behavior of how you deal with in a partition, there's probably more than 2 settings, but yes, 2 would cover a lot of the world. You're right. Yeah, you are right.
So let's take 2 more questions, and then James will be up there with us.
Yeah, looking forward to it.
What's your opinion on using flash as a cache technology in front of disk? Limitations and opportunities, I would like to know.
Yeah, so the question is, does it make sense to put flash in front of disk as a cache, so you're just cooling the workload on disk? It does. It does. The problem is, it depends. In order for that to happen, you need a lot of skew in the access patterns. And so if you have old historical data that's very cold, then it should be on disk. The problem is it has to be quite cold before it makes sense to move it off to disk, because the ratio of the cost of disk and the number of IOPS it can support versus the number of IOPS that flash can support and the amount it costs. I think it goes back to an earlier question, is the way that I think the game will be played is, first of all, if it's very cold, it should be on disk, and I believe that will happen. The second thing is, for what you do put in flash, because you're capacity constrained now, it is tight. Disk was never capacity constrained. This is capacity constrained, so then you're going to run dedupe, then you're going to run compression, then you're going to do every possible thing you can to get more capacity out of that, because CPU is relatively free compared to the value of capacity. And so I think the combination of running dedupe and compression is going to allow more to be in flash. And the second thing is yes, for that which is very cold, it will end up on disk. And people always say, well, what about in-memory databases only? They're just never big enough. What about in-flash memory databases? It's just never big enough. Ice-cold data has to migrate off. And ironically, most of the data in the world is actually write-only. Most data never gets looked at. And write-only is perfect for disk. Absolutely perfect. Just one more question, sure.
So the power companies near New York, like Consolidated Edison, when they generate electricity, they also pump their waste heat into, they sell it to the city of New York to heat people's homes.
Yes.
So what types of technologies are being looked at for like using waste heat from data centers?
Great question. So the question is, when you have 10 megawatts in a single center, that's a lot of heat. That's very valuable. It seems crazy that we're going to spend 20% of all the money we spend is pulling heat out of a building. That's what that model I showed you earlier was. That makes no sense at all. Why can't we monetize that heat? Well, first is it's hard. It's low-grade heat, and so for most centers, it'll be when it leaves the servers, it'll be order 105, 115 degrees Fahrenheit. So it's relatively cold by heat generation standards. And so it's low-grade heat's the first challenge. But there is a lot of heat there. Ways that I've seen it used and things that have some merit is if the data center is in a downtown area where there's lots of office space nearby, totally makes sense to use that heat to heat those buildings. The problem is it transports poorly, and data centers are most economically placed a long way away from people, and so that idea is not heavily used. I can point to a few places that are doing that, but it's not very common. The one that I like is if you're off in the country somewhere, like for example, a lot of data centers are built in cold areas because the cost of cooling in a cold area is wildly lower. Well, the beautiful thing is many of these have it's a great environment for growing high-value crops. And so it might be the case, like there's a lot of, if you look at around the BC border, there's a lot of tomato production because tomatoes are a very valuable crop. It might be the case it can be used in agriculture. The key problem is it doesn't transport well, and it's very hard to get to extract power from such relatively cool temperatures.
Now we understand why they've moved into Amazon Fresh. They're going to be growing their own vegetables.
You're growing your own vegetables, exactly right.
All right, James, thank you, and we'll see you all.